Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Hi, I'm Dave Whitehead. I'm your host for Schweitzer Drive. According to the North American Reliability Corporation, or NERC, the rapid interconnection of the bulk power system with inverter-based resources, or IBRs, is one of the most significant drivers of grid transformation and poses a high risk to the bulk power system reliability. Today, we'll be talking with Dr. Normann Fischer to discuss what makes IBRs, quote-unquote, a high risk to the bulk power system reliability, and what can be done to minimize these risks. Norman is a distinguished engineer and vice president of R&D at SEL, where he leads a team of more than 400 people focused on the invention, development, and support of SEL's protection products and technologies. I've had the pleasure of working with Norman for more than 20 years because he joined SEL in 1999. Norman doesn't seem like that long ago. He's authored dozens of technical papers and earned more than 30 patents. He earned his BSEE from the University of Cape Town and his MSEE and his PhD from the University of Idaho. And he's a senior member of IEEE. Norman, welcome. Thanks for taking time to join me today, and let's jump right into this. To begin with, our topic is IBRs and how they integrate into the electric power system. Could you tell us what an IBR resource is? And remember, my mom's listening to this podcast, at least I hope she is, so you got to make sure she understands at the end of your explanation.
Well, thank you for inviting me, Dave. So an IBR means you take the energy source and you connect it to the bulk electric system through a set of electronic switches. So let me explain from a very simple point of view. Most folks who want to charge a battery plug the one end into the power supply or into the socket and the other end into the battery. What happens is that AC power gets converted by means of an electronic switch to DC and then charges the battery. We call that a converter. An inverter does just exactly the opposite. It takes the DC power from a battery and then converts it into AC power, or it inverts it. So an inverter simply does is take AC or DC power and inverts it into AC and feeds it into the bulk electric system or the power grid. That's what an inverter is. So an IBR source means it's a connection between the power source and the power system via that inverter.
So I guess if we're talking about it from utility or grid space, then it's just a way of identifying what kind of source it might be, versus a typical turbine or gas turbine or hydro plant. We're talking about an electronics-based source versus our traditional spinning resources.
Correct. You don't really connect the turbine up. You connect the synchronous machine or the generator into the power system. Yep. The turbine drives the generator, and it usually goes through a step-up transformer and then onto the power grid. Here we go through an inverter-based resource, an electronic set of switches into the power source.
Where do we find inverter-based resources these days in the power system?
The answer is actually everywhere. So we start from what they call behind the meter, which is your rooftop solar. Then you go into the distribution systems. You'll get that typically, those are mostly your PVs and your solars. And then if you go into the bulk electric system, you will see then comes the wind turbines and your large solar plants. So you have them in three distinct locations, in what we call behind the meter, which is on your house, on the distribution system, and on the bulk electric system, which is on transmission.
And I think what we're also seeing these days too, or at least there's some work being done, is what I call grid scale batteries being introduced into the grid too.
Correct. And the issue with IBRs are, if we can say all of these, are that they what we call intermittent power sources. So if you remember back, we were talking about hydro, you were talking about gas turbines, you were talking about coal. That's what we call dispatchable load. It's available 24/7, 365, whenever you need it. Well, when the wind doesn't blow, those wind turbines don't turn. And if the sun goes down, those solar cells don't work. But you do want to cook at night, watch television and all of that. So you have to store the energy somewhere. So one of the things of storing energy is in batteries. Now, we can debate for an hour here is that's the most optimum way. But I'll give you an idea. Even if we built all the batteries we liked in this world, we could supply the US grid for maybe 5 minutes if we're lucky.
Yeah.
Right. And if we really want to be serious about storing energy in bulk, I think we all have to turn towards what we call pump storage hydro. And that's what the Australians are doing. They're building a big 2 gigawatt plant to store their inverter-based resources in for make it dispatchable to use at night and when days there when it's no solar power or no wind.
So let's get into a little bit more of the technology sides of IBRs. We kind of touched on it. So you explained to us that the IBR is really an electronic device that can take DC, whether we're storing it at 100 volts or 10 volts or whatever, and through switching mechanisms of the power electronics, create 120 volts AC at whatever voltage, 480 volts or whatever it might be suitable for interconnecting with the grid. How does the electricity that gets the AC electricity gets generated by IBRs differ from traditional means of electric generation?
So when we have electric generation and the flux and we move it through very periodically at 360, we get very nice sinusoidal waves. We don't generate
and when you talk about flux, what we're really talking about here is spinning machines, stuff you'd find at a hydro plant or
a rotating piece of machinery.
Yeah.
Right? It produces a very nice, clean sinusoidal wave at the system frequency that you're looking for, and it doesn't create any byproducts almost. And I'll explain what I mean by byproducts. When you take DC and you switch it, because what you really do, the power gets generated at 100 or 200 volts. Typically for a PV, it's 480, and for a wind turbine, it's 690. Now, we don't push that into the bulk electric system. So what they do is we actually chop that up in a way. And
the DC signal we're chopping up.
Right. We chop that up. It's called, we don't want to use any more terms in here. I don't want to say it's a switch mode, power supply, all of that. But what we chop it up and that becomes pulsating DC. And then we send that into a transformer and that transforms it to the voltage level we need, which we then feed into the bulk electric system. So just as we would have on our normal conventional AC plants, we have an interface which is called the transformer between the power system and the source. We still have that. In addition, we still have to have the inverter itself. And when you actually chop up the actual DC, you create a lot of byproducts or harmonics. You have to put in filters and you don't produce a clean fundamental frequency, voltage and current, which you inject into the system. So those do come in and they have effects on that. The effects are larger than this, and we start seeing it in our industries. As you have a large piece of rotating machinery, you have inertia, and that allows you to ride through bumps and switches. You no longer have that when you have your inverter-based resources. You've removed that inverter, and you've basically said you've set your inertia, your rotating mass to zero. So anything that happens, you will see the system will react a lot quicker to it.
So really just to play back what I heard, I have the traditional generation source, whether it's a gas turbine or a hydro. I get this big spinning meson, and it makes these nice continuous sinusoidal waveforms that they get put out on the power system. Very clean, as you pointed out, right? If we're generating at 60 hertz and we were to look at the output in the frequency spectrum, we just have this one line right at 60 hertz. Contrast that to an IBR, which is really I'm going to call it a digital process, if you will, because if you were to look at the waveform of an AC signal being generated by an IBR, you'd see a bunch of little steps coming right out of the inverter itself. And then to your point, we got to put it through a bunch of analog filters, inductors and capacitors to smooth out those little steps we'd see as the power electronics are opening and closing to create this AC waveform. But we can never fully get rid of those things. And so what we have is, I'll call it a messy spectrum where you have harmonics and other inner harmonics on this new waveform we created.
Absolutely correct. The harmonics we could take care of at a certain amount, but the interharmonics are a lot more complex and we'd have to tune each filter for that.
And so this is great to have an IBR because it now allows us to take these new energy sources, whether they're the solar or wind farms or batteries, and connect them to the bulk electric grid. Yay. So what are is that the main advantage of an IBR? Why IBRs versus some other way to generate electricity?
I think the advantages that IBRs have is that they are green. They don't produce any byproducts like carbon dioxide, and they don't create any pollutants. However, they are not the densest form of energy we have. I think the densest form of energy, and sometime we're going to have to talk about it, is actually nuclear energy. And I think the problem is we've always given nuclear a bad rap because of the few instances we've had. But if we look at it, if you want to really move a bulk piece of equipment, like you take an aircraft carrier or a submarine, you used to power it with diesel, but that's not efficient. So what do you power it with nuclear reactors? So I think if we want to really have a power system where we can say we have reliable, clean energy, we're going to have to look at nuclear. We have come to the point, I think, that we've built the biggest wind turbines we can. As you know, in a wind turbine, you have to have the diameter to give you that energy. If we build those turbines any bigger, we won't be able to transport them. So it becomes to a point is how big can we make the blades until they are no longer transportable? And so we're reaching up, and I think if you look at it, how many wind farms do you want to build? And how many PV installations do you want to build? From a point of view of energy density, those are some of the lowest energy densities we have.
But I'll make an argument, since we're talking about the advantages of IBRs. You and I have flown over Nevada, and we've seen huge solar farms there. It's like, it's not a bad place to put a solar farm, because I don't know what else you're going to do in the middle of Nevada.
Correct. Now you bring out another point, is if I produce that much and I have, all of a sudden I need that energy, right, and I become reliant on it, what do you do on a day if I don't get it, or at night when I need that energy? What do I do? It's like the same thing is I rely on this wind, but in the middle of summer, in the middle of winter, no wind blows, and do you want to freeze now? So you're going to have to store that same amount that what you have in the IBRs. You're going to have to store somewhere. Where are we going to store?
Well, that's where we get back to pump storage. Sounds like a good idea, unless of course you live in Kansas where there's no hills to put anything. Or batteries, which are not necessarily efficient.
So what you're telling me then is, and you're quite right, is if I build this large amount of IBRs, I've got to build a storage plant of equal size, and it's got to be for that duration. So the thing is, if I'm going to say I have to take care of 3 days in winter when it's really cold, and this is 1,000 megawatts out of there, well, I've got to have 72,000 megawatt hours of stored energy available.
Yep. I'm not saying it's a perfect system, but
no. And I see a power grid where we're going to have a mixture. We'll have a mixture of all of this, and I think everyone has an important role to play.
Back to some of the benefits of IBRs. One of the things that I think is pretty interesting about an IBR source is that it is, since it is an electronic piece of equipment, we get to control all facets of it, right? So if I want to create bars, leading and lagging, power fact, it's like, man, that is totally controllable now. So there are some benefits to having large scale IBRs.
Absolutely, but now you have to be very careful that you do that with all the other IBRs in sync. Otherwise, you're going to have what we are starting to see on this grid, are some synchronous control interactions between the control systems of the different IBRs. And what we now see is we see these low frequency oscillations on the power system, and we can't explain where they come from. So yes, it has its advantages, but nothing is for free. So we have this, like you're saying, we can wrap it. I can also say that I can get rid of out of step conditions out of a power system where the power systems pull out of synchronism with each other. I can prevent that. But now I bring in another issue. So everything has its challenges, and us being engineers, we can address all of those, but we need to realize that they're there. So what I'm saying is there's nothing for free. So even though we say that we can get the wind and the sun for free, but is it really for free for those systems?
That's why us engineers have jobs, right? Is to go solve problems. Sometimes we're solving problems we create, but it's kind of fun to think about how we integrate IBRs, not just in individually as a unit, but rather as a system of generation sources.
So the other question we can ask on the IBRs is, why did we then go to AC? Why, if we are generating at DC, why don't we leave it at DC and go start on DC transmission? That's another thing we could look at, especially if we look at more rural settings where you have behind the meter, let's say in a housing development. Do we really need to convert that back into AC, or could we leave it in DC?
Well, which loads would be driving then inside our house?
Yeah, but if you look inside your house, most of your loads are actually DC.
Oh, but now you're looking way into the future, because I got to get rid of all the front end of my TV. Doesn't plug into a DC.
But it would, because you go through a normal rectifier, which will then. But
what I'm saying is I gotta modify my TV. I gotta take all the AC middleman out of the equation. And you know what? I bet 1.44 comes out of my battery, but that thing's gonna want something that's not 1.44. So I'll have some other kind of converter.
And these are things we're going to have to look at, is why do we convert it? Because every time we convert it, we lose a certain amount.
Oh, yeah. Every conversion will have some loss factor. Not everything is 100% efficient. Nothing is 100% efficient. Maybe I should rephrase it that way. We talked a little bit about the advantages of the IBRs and a little bit about the disadvantages of IBRs. Conventional power plants today have an expected design cycle of, say, 40 or 50 years. What do you think the life expectancies of an IBR is going to be?
So that's interesting that you mentioned that. So if you look everywhere in the literature, they say anywhere from 20 to 25 years. But
for IBRs?
For IBRs, but that's not the whole truth. They say that your gearbox, which takes the most of the pounding for a wind farm, has to be replaced around about every 10 years, and so do the blades. Now we say IBRs, they don't produce any greenhouse gases or anything, or they're carbon neutral. That's correct. But what do we do with those blades? There's no ways to recycle turbine blades. You know what we do with them at present?
Leave them there?
Yeah, we actually dig a hole and bulldoze over them.
Yeah.
So now tell me again, we have no carbon footprint. And the other thing I could ask is, what is the carbon footprint to produce that IBR? So typically the life expectancy is about 20 years, they say, but you have to do periodic maintenance on it. Whereas if you look at your coal-fired or gas or what, they have a 40 to 50-year life. Yes, you have to do maintenance on them. But the difference being is, if you look at the amount of megawatt hours generated out of a gas turbine or a nuclear or a coal plant, it'll be a lot higher than what you'll get from the megawatt hours produced from an IBR. So I think we are still got to do the economics on it, right? I'm not saying we shouldn't be good custodians of the earth and look at what. I do think we should be very well aware of what our energy needs are, but I think for an economy to survive, we need sustainable, affordable energy.
Reliable and dispatchable.
Exactly.
Yeah, I agree. You especially are in the protection business, right? And have built a career on power systems that, for the most part, use traditional spinning, rotating machines that create our electricity to design countless ways to detect faults on a power system based on those generation sources. With the introduction of a lot of IBRs these days, how does that impact the detection of faults on power system? And how do you go about addressing those things? Because they're not going away, and they're getting intermingled with traditional sources.
So if we used our traditional methods for protection, except for line current differential or for using a differential principle, most of them wouldn't work, because the IBRs, first of all, they don't have the inertia, so the frequency could collapse quickly, and they don't give us the current that we want, the fault currents, because the switches aren't designed to handle much more than the fault currents. So we are seeing, if we're going to use the energy that comes out of the sources, we're not going to have much success. That's why if you look at the protection, what we're looking at, if we look at the transient quantities, that means we're using the energy that's stored in the power system, like from transmission lines in the actual shunt capacitances and that. We use that energy, and it's only for a short time, for a cycle or two. We can use that as a protection principle because that's independent of the sources. The power system generates that for a short amount of time. And those are the signals we are looking at to do the new generation of protection on these. Now, the caveat to that is good for the first, but if we had to use that for backup, we're going to have to look at a different way of doing that.
What are your ideas there?
So there's a few ideas is that we were looking, is like I said, there's line current differential we're looking at. We were looking at things like the voltage depressions and things. So we are looking at different aspects. But for right now, the good thing about being a hardware engineer like you, Dave, is you can play with the power system, or you can play with your electronic circuit board. It's very difficult for me to tell one of these wind farmers, hey, I'd like to play with your system and throw a few faults on you. They're going to look at me as if I lost my marbles. And so what we are doing is we can monitor and learn from this. And I think we're learning a lot. And what we've learned most of all is that every IBR behaves differently because they no longer abide the laws of physics that we used to. They now abide the laws of the engineer who wrote the control equations. And so I might test something and protect it for this version of firmware. As soon as they update that firmware, what I have done may no longer be valid. So I think we're in a stage of learning. So right now, I think we are learning how these IBR or inverter-based resources are behaving during what I call abnormal power system conditions. Not just faults. There's different things. You have switching conditions or you have a low voltage, how they behave.
Hey, do you I'm usually never a fan of regulation or compliance, but do you think there should be some level of standards for IBRs as opposed to the wild west where some software engineer thinks he understands physics and just design his IBR to perform?
And that's being done. So if you look at 1547 was a set of standards that basically states how the IBR should behave on a distribution system.
Yep.
We're busy with crafting P2800 of how they should behave on the bulk electric system and the interconnection. There are certain requirements to ride through.
What are some of the attributes then that you're looking for those standards?
So some of them will say how they have to behave. So if you looked at your first generation and they call them grid forming or grid following inverters, They basically just followed the power system and injected the power and voltage. As soon as they saw a fault, they disconnected themselves. That means if I came back and reconnected after the fault had cleared, I would be missing this large amount of power. So they said that's not allowed. Then they said, okay, you have to have a certain amount of under voltage right through. As you know, if a fault occurs, the voltage drops. One first thing those IBRs is through themselves to protect themselves offline. They now got to stay. So and then we also stated is that for the grid following, they also said, okay, it didn't produce any reactive power. They kept on pushing out active power. And during a fault condition, you need a certain amount of reactive power. They didn't inject negative signals. So we are slowly but surely stating how these machines have to comply on their performances during these conditions.
Well, that's interesting. And it's an evolving technology, right? As I recall from the IEEE standard on how we, 1547, how we manage distributed resources. Originally, the reason you had that IBR, the distributed resource, take itself off the line is because there was probably only one. It was really a safety condition for alignment so that, if upstream protection, traditional protection isolated the fault, but the IBR kept the line energized, that could be a hazardous situation for alignment trying to troubleshoot where the fault was, right? It'd be energized from the backside of the feeder versus the incoming side.
Correct. And so that was and then initially they weren't very large. They didn't make much difference on the power system because the bulk system was still, and that was all rotating. Now, as we see that inertia go further and further away, we can't have that anymore. They have to stay in. And you will see that the inverters now have gone from what they call grid following to grid forming.
And I think that's the difference, right? Everybody wants to have these microgrids, and the first thing that would happen is when you need this distributed resource, it would take itself off because that's what 1547 would. Now you can separate from the bulk grid and have these IBRs run your local microgrid.
And so what's happening is they said that we're going to just have the IBRs on their own, and that didn't help because we needed voltage support. So you will see coming into the system together with there's a large ingression of synchronous condensers coming back because they, during fault conditions, have to provide the VARs to write us through. I think we're not there yet. We're making slowly steps. How do we make or get a more robust power system with just IBRs? I mean, if we take the last of our rotating masses off, I think we still have to have a stable grid. We'll probably see a different grid than what we are seeing today, or different set how the IBRs behave than today.
You were in charge for a day. How would you manage that, right? If you were left to IBRs, how would you go about coordinating, synchronizing?
The good thing about an IBR is you can give it an instruction and they'll all come into it the same. You can give them, okay, here's a frequency and voltage set point. This is what you start with. Right? Like I said, again, we have to make sure that they don't oscillate against each other. But I think the grid of the future that I see will be a mix of IBRs and still conventional. I think we are not going to be able to get away from it. I think our power system will have a large ingression. I also think of nuclear power plants because we do need dependable power. How are we going to make it dependable? How are we going to store that amount of energy?
Yeah, we've done previous podcasts, and I've made the on nuclear power, and I've made the assertion that I think if our objective is reliable, dispatchable electric power, and we want it zero carbon emitting, you end up at nuclear. I think I think intellectually you have to end up there. The question is, how do you, but that's not going to happen tomorrow. So then the question is, how do you get from where we're at today to that particular endpoint? And it's going to take a number of years before that.
The nuclear technology in the last few years has evolved tremendously, especially if you look at the modular pebble bed reactors they're starting to build out of this. And you brought out something else. Okay, if we want zero carbon, it means we're going to remove all the cars out of the U.S. power, out of the power system. And if you look at the amount of fuel sold last year, for us to do that, we'll have to double the size of the power grid we have today. So if we make a statement that by 2035, we want no more.
You can't sell a new car?
Internal combustion engine, no more. We'd have to, in 10 years, double the size of our power grid today.
I think those are aspirational goals by politicians. I just don't think the physics or the economics can get us there. This brings me up to we're talking about IBRs, right? And I know a lot of forward thinking folks have proposed that I use my Tesla or my Ford F-150 Lightning as an IBR that can backfeed the grid in times of stress or duress or whatever. What are your thoughts on that?
I think that can be done, but now we are going to have a much better method of actually control or dispatching those loads. Can you imagine right now, if you look at the complexity of keeping the power system alive, where we have stationary sources? Now imagine how you're going to control the power grid and manage it if you have mobile ones. You don't know where there's going to be.
Who's best to do that? Is that with a traditional utility? Is it some other?
I think it'll take someone else. I think the utilities are looking at how we're going to do it, because it's the same as behind the meter. You can produce enough power for yourself and export. So if you found out what happened in Europe, I think it was 2 summers ago, they had enough solar power that everybody exported onto the grid, and the grid had to start shutting off some of the base loads.
Yeah. Where's the power going to go, right?
Yeah. And so that's the other problem. If I have all the wind turbines running, are they now going to turn them around and we put them in motoring mode and they're going to generate wind?
It'll cool down, right? We'll take care of global warming that way.
So I think that there's a lot of challenges we're going to have a look at in the power industry itself. Is we're getting a new technology, IBRs. We're going to integrate them. Yes, we are. But we are going to have to also be honest to ourselves and say, what do we do when the wind doesn't blow or it's dark? How do we store this amount of energy in bulk? Are we going to say everybody has an electric car, but then how do I charge? Somehow I've got to get that energy into the electric car.
Yeah, I'm a little bit skeptical about the electric car just because of I don't want to walk out of my garage in the morning or something like that and find out for some reason my car did not get charged because it was not on the right cycle, and I don't want the wear out on my battery of the deep discharge or something.
So I don't think the electric car is the actual issue here. Building an electric car is actually simple.
I don't think Elon Musk would say that, but I hear you on that.
It's not as complex as you don't need the complexity of a gearbox and all that. No.
Yeah,
exhaust, all that.
I agree there.
The complexity, I think, is how do we store the energy and how do we get that electricity to the points we need it? So imagine if all of a sudden I said to you, everybody in Pullman's going to have an electric car. Vista is going to have to increase the power supply to Pullman.
Well, a few studies I've seen on this, as it relates to IBRs, is for every car I put in a car charging at peak for peak charge kind of stuff is the equivalent of a household load, right? And so you can just say, if nothing else, at some level, I've got to almost double my distribution system.
right? And then at some point, you're going to say, can I move that amount of power in the distribution system? Let's say in Seattle, you'd have to bring the 500 kV network into town, which you can't do, right? So it's going to have to go underground and with cables. And so now it's going to get expensive.
At least 3 times as expensive as building overhead.
A factor of 10 at least. The cable's 10
I was talking to somebody for a 230 kV, right? And this was out in the desert, and they said it was 3 times as much to bury it. So maybe they were getting a deal.
Yeah, maybe to bury it, but buy the cable is much more expensive.
Oh, this is installed cost. Yeah. So we talked a little bit about where IBRs are evolving. Any other thoughts on IBRs?
I think they're here to stay, and we're going to have to learn how to integrate them. And we're going to have to help write the regulations to how they have to perform.
And do you think we're moving from let's call it the wild west of IBRs to more of I'll call it a mature technology or mature?
I think so. I think we're going to get a lot of standards written. Let me give you an example. When the electricity system started here, I could say, what frequency am I going to generate? Some guy says, I like 25. The other one says, I like 16,667. The other guy says, I have 50. And then we standardized in the US at 60 hertz and the rest of the world went to 50. So I think there will be certain standards because we have to interconnect all of them and we have to know how they perform. But till we get there, I think there will be a lot of water will flow through the Nile until we get to a point that we can say, okay, we can really integrate these IBRs into the system without any issues.
That's interesting. So here, I guess the upside, this means we're going to have another podcast to talk about the evolution of IBRs as it continues.
I think so. I mean, so if you look at it, IBRs have been around for a while. So if you look at the first generation of wind turbines that came, the type 1s that were in California in the late 70s, and how much they've changed. The whole technology changed. Oh, yeah. I mean, they weren't IBRs at that time. You connected straight into the generator if you wanted to at that time. And it was you could say it was an induction generator. We had to supply the capacitors. That was the type 1s. Then we had the type 2s. We actually that's when they started what they call the defigs in there. Then we had the type 3s, which are now mostly on land-based. Now we have the type 4s, which are mostly out. Those are totally IBR connected. Those are the ones that we have out on the oceans. You look at PV, solar has come in, even though we've had solar for a long time, but the big solar panels have been. So I see there's an evolution that's coming with that. Yeah.
Well, that's exciting. Norman, thanks very much for your time. I appreciate the discussion. And like I said, I'm going to have you back when we, as this IBR technology continues to evolve and as we integrate more and more of it into the bulk electric power system. Thanks again for your time. I appreciate it.
Thank you for inviting me, Dave.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.